Okay, we have some questions about multiple values of a dependent variable. This is a big MNIST data set. MNIST, it is a image data set that I'll show you in just a minute. It looks something like this. If you run a DF head on the first 5 rows, very first, they're handwritten digits. Okay, the way we all write our digits, they're different. You'll notice you've got 784 features because this is a 28 by 28 matrix that they use for each image. Now, those are pixels. And so you see here what you've got. This happens to be the label right here, which is the actual number. The first instance is a 1, the third instance is a 4, etc. Now, 0s to 1, this is essentially, does that pixel have any light? 1, yes, 0, no. So it's got to identify it. So all you do, you're going to load up the exact same code libraries, except in this particular case, MNIST is so well understood and used, you can import it right off TensorFlow. So this happens to be just a different way to run this. So you come down, you load it, and it gives you the size, which is, what is it? 32 million cells. And you pre-process, I normalize the values to the range of 0 and 1s. That's because they're 28 by 28, as you see here. Then you flatten it. This is just strictly so I can look at images. You're going to compile it like we did last time. Then we only ran, I think, only 5 epochs because it's so big. Test accuracy, 97.8. So you come down and you're going to make predictions as usual. Then I want to look at the precision. I'm not too concerned here because it's identifying the images so well. If you'll notice, accuracy, precision, and recall and F1 score are all the same. What's interesting here is the confusion matrix. This is obviously coming across. If you'll notice, pretty much very nicely done, but you'll see where things really mess up. The 3 and the 10, see 0, 1, 2, and this is, let's see, 0, 1, 2, 3, 4, 5, 6, 7. So the 2 and the 7 get fouled up the most, et cetera, et cetera. So the reason I showed you this is when you set this up, if you do have multiple values on your dependent variable, you've got to figure out how you want to set that neural network up. In this particular case, this vector here is just because you're doing image processing. Notice the hidden layer has 128 neurons in it. This particular, the ReLU activation function just happens to go along with images. The output layer is 10 neurons, 0 through 9. So I'm looking at a probability that if you got 0 through 9, the highest probability hopefully would be correct. So I just put that in there so that all you realize, I want you to realize is, it's the way you set this up. There's only, let's see, 1 hidden layer. So what you can easily just tell your neural network in the code, I want 2 or 3 hidden layers, and it'll go and do what you tell it to do. Then you can decide, and you can ask it for that. Then only run a couple of epochs and see what happens. But 10 neurons in the output layer is where you want to be with that. And I just put it there because the only thing you have to change is that particular output layer. And you decide how many input layers you want to put in there. So I didn't want you to think that this is the neural networks are all locked in like that. If you've got multiple output layers, you can do logistic with more than 2, more than a binary. Some of you have multiples. If you go out to GPT, it'll tell you how to do multiples. But things start getting a little squirrely with the S-curve. So I would skip logistics if I had multiples. Just a thought. I've been getting questions on what to do about that. Y'all straight on this? Not a lot to it. Oh, let's see. Let me get back. Let's do this one is. This one down. Okay. Little expanded notebook here. These are what the labels look like. This is literally taking our handwriting. And what you do is you just split this up 28 by 28. As you can see, some of these are lighted, some of these are not. And it picks them up. It also will do shades. And so you can see how people write the numbers. And again, there are 32 million cells, large database. So you're coming along the same thing here. This is the description of why you're rearranging the data. Of course, you'll do your usual labels here, up 0 to 9. Split the data, do a sequential model, feed forward. Then we're going to flatten those images. Now, in this case, we work with 2 hidden layers. I ran deliberately that over. I ran it with just 1. So in this particular case, it said that good starting points for moderately complex problems such as image classification and 128 in the first and 64 in the second. Okay. 128 in the first because the actual handwriting has more alignment to basic features. And the second layer has fewer neurons to refine those features. So what we're trying to do is balance complexity with efficiency, of course. So I want to balance overfitting from underfitting. So as you come down, and I'll show you that in a minute, there's your hidden layer set up. Hidden layer 1, hidden layer 2, the output layer with 10, compile the model, and so forth. Okay, in this case we ran 10 epochs, and as you can see, it's still grinding away merrily. And I'm up with the second hidden layer. I've gone from 97% accuracy in the first model that we ran, the other notebook, to 99.5. Ran pretty quick. So the test accuracy is 97.3. Then I want to look down here at the confusion matrix. Now, again, 5s, let's see, what is this here? 3s and 5s get fouled up, as you'd expect. 9s and 4s, depending on how people write them. That's the deal here. What I want you to do is translate this in your head to facial recognition. Okay, so you go back up here, or any image recognition. I just mentioned facial recognition because that makes people nervous. So if you take an image of a face here, and of course, here we're just using square pixels and how dark or light they are. With a face, you've got a whole lot of other things. So instead of having 784 input features, you're going to have thousands. Okay. You're also going to run deep neural networks, and that turns out to be a very interesting, if you're, say, a police officer, what do you suppose the confusion matrix looks like? Look, you're about ready to go arrest somebody. And you're going to have to look at this confusion matrix. They don't. They just look at the probability. And that's a real concern Okay, take it down a step. An X-ray, cancer, no cancer. You may not have as many features as a face, but clearly you're still doing pattern recognition. Okay, that's all this is. Okay, this is a nice baby look at some real serious real world applications. All right. Let's try this. I'm going to do this again. All right. So you get through with all your models. You've been through the algorithms. Got your data sets. Y'all have already started cleaning them. Some of you are done. So you got your models set up. You've applied your clean data. You start applying to the algorithms. And then you get to the point where you've got, you've decided what you want to use. Some of you already run your neural nets. Okay, so then you get these challenges, which are not particularly straightforward. So we're going to have to look at bias. So what are you trying to do? With the models that we have, remember we don't have data flows. We have static data sets. So you're going to have to approximate a real world problem with a simplified model. This is always the case, whether you have a static data set or your data keeps coming in. What happens to the real world problem as data keeps coming in? Nothing. Real world problem's still there. Whatever you're trying to do is still there. So what you get is, hopefully, as your data continues to come in, your model becomes less simplified and your precision goes up, your accuracy. This would be great news. All right, but if you have high bias, you've got poor performance on training and testing data. There's something absolutely going wrong. So you got to reduce this bias. This is on the computer science side, but who picks it up? You guys do. Okay? Now, the data scientists may notice bias and come to you, or you may notice it and come to them, but it comes out in business terms. And so you can develop more complex models, you can add more relevant features, and you can adjust the hyperparameters. This is what developers can use to reduce bias. Now, variance, this gets to be a little more subtle. In this particular case, what's noise in the training data? That's errors. It's variance. Okay. It'd be great if all our training data were the same. That's not happening. Okay, not even in here. So if your model is sensitive to what you're seeing in training data, errors, a lot of variance, outliers that we've talked about. If you're high variance, you've got an overly complex model. Now this is interesting. Your model's overly complex, that means it learns the training data too well. So it doesn't generalize to the test data. Remember, we're using 80-20 splits in here. You guys can adjust that if you want to. So I overfit, not getting generalization, that's high variance. Okay, so what can you do? You can simplify your model, kick up your training data, which you're going to do anyway in the real world, or you can put regularization techniques to constrain the model's complexity. That is computer sciencey stuff. Increase the amount of training data is great. Simpler models. Now what's going to happen with a simpler model, developers will come to you guys and they'll say, is it okay if we kick some of these features out? And your question will be, since you've been through this class, is which ones are significant? Okay. If you hadn't had this class, you'd say which ones make sense to me. You guys will do both. Okay. All right. So this is what everybody has to deal with. The bias variance trade-off. There's a balance here. If you reduce bias, variance tends to increase. If you reduce variance, bias tends to increase. They just do this. Okay. So what would you like to do? This be a great model right here if you found some optimal balance. Now, it is possible to do this in almost every case. If you've got the money, you've got the electricity, and you've got the time. What's a great balance in fraudulent credit card transactions? What am I balancing? False positive, false negatives. Same thing with cancer diagnosis. Same thing as a book recommendation for Amazon. The recommendation engines, that's what you're balancing every time. Now that's oversimplified, but that's essentially what they're doing. And by the way, who makes the final decisions here? You guys. All right. Now, back to overfitting. We all now know that your model learns the training data too well. It captures, in other words, it's memorized the training data, so it captures the variance right along with the pattern. Okay? This variation, in most cases, is irrelevant to the underlying patterns, so this is when you get overfitting. It doesn't generalize to your test data. Okay? So what do you got? You got low bias and you got high variance. Well, you're doing great on training data like a 0.95 and poorly on the test data, 0.62, which we've seen already. Model's too complex, too many features, we talked about that. Okay. Remember, simpler models, more training data, cross-validation, and so forth. Okay, underfitting. Got a model that's too simple to capture the underlying structure. So now I'm back to high variance and high bias and low variance. They oversimplify the relationships within data. That is classic underfitting. Now, it's not always bad, as we'll talk about. So this one was overfitting. Underfitting is, I've got probably, I may even have the wrong model. So again, you can make your model more complex. Okay. Well, by the way, who tunes hyperparameters? In this case, the developers would, but you guys know what those are. Okay? All right. Here's a nice scatter plot. We're back to the two-dimensional world here. Here's the amount of sales. Here's your advertising budget. As you would expect, just off the top of your heads, because you guys are all marketing wizards, if I spend more on advertising, I would hope the sales go up. I'd be depressed if they went down. Although some of the ads that I've seen on television lately, I don't know who thinks this stuff up. So there's your training data in blue. Okay, test data green. This is not an 80-20 split. It's just I want to show an example. Okay. All right, now, in this particular example, I want to point out, as you guys know, there's what will happen is you can increase the size of the advertising budget and you will end up getting to the diminishing marginal returns. So you'll get declining or decreasing increases in the amount of sales is what you would expect. Now, there's a really nice regression line. Everybody in here knows how to do regression lines. Okay, but y'all get that 8th grade. I mean, that's what we've been doing ever since. Okay, nice line. Now, here's the deal. You can fit this regression line through all these points. Forget test, forget training, and just say, there we go, because we've minimized all these differences, okay? All the distances between these points and the line. And as always, if we just take the distances above and below the errors, they would add to 0 with a well-fitting regression line. You've got the intercept over here naturally. You got to square them, and we do this. We minimize the squares. Okay, this is great. This is what we used to do in the real world. All right, let's go back. Remember, blue is training, so let's fit it. What I really want to do is I want to get a fabulous regression line. The training data. That's a perfectly legitimate regression line. Takes some math, but that's, as you know, is perfect. Everybody's happy. Your developer comes to you and goes, I got an R squared of 1.0. I've had that happen in this class before. It's fantastic. Somebody shows up and says, would you check this for me? I got an R squared of 1.0. And I've done it myself. What's wrong? I'm so grossly overfit, but in layman's terms, this is great, but what about the next data point? Well, the next data point you better have, is this here, you better have a map to turn this corner and go down to it, okay? Not logical, but this is classic overfitting. Okay. All right, now we include the test data. And if you'll notice, This is the original line. We've got this line here. And so the regression line from the training data doesn't fit the test data. Here's the original regression line through all the data. Notice where we are. The green dots are the test data. Okay? The blue dots, training data. All right, I essentially have no residuals there, but notice how large the residuals are on the test data. So that's what happens. Training data, residual 0, test data, huge. Okay? You'd figure that on overfitting. Notice straight line, lower sum of squares. The difference between the test data and training data fits or variance. Curved line has low bias and high variance. This line, low bias, high variance, and it's hard to predict how it'll perform in new data. Naturally, it's actually impossible. The regression line, this thing, okay, was it high bias, low variance? Yep. So it'll provide, let's see, it might only provide good predictions, but they'll be consistently good. Okay, this means, as I bring in test data out here, it may not be perfect, but it's a whole lot better than trying to do that line. Okay, now, this is fine. Back to scatter plot. Now, remember, you're going to get, by definition here, our business problem is, as I add advertising budget, I get to diminishing marginal returns, and the amount of sales increase will start to ease off. So it won't increase as much. So, ostensibly, you could put a line in, something like this, just arbitrarily, to show that as I increase advertising budget, the amount of sales increase starts declining. Doesn't mean that sales decline, but the amount of increase declines, which is essentially what this red line is trying to do. Well, you're overfit here, okay, with this line, all right? Now, with this line, you're underfit, because I got low bias, high variance, and overfit, and high bias, low variance. So this particular line, again, which is trying desperately to show that relationship that the increase in advertising start tapering off with sales, that you end up with, you say, well, in this particular case, you look at it, you say, if I'm overfit with this red line, because I'm considering it, then because I'm trying to get to that model where it does decline, then you're out here and you say, overall, that underfit line works better. And that's the way bias and variance looks. So the regression line doesn't accurately fit the true curvilinear relationship, meaning that it's underfit. Too simplistic, but it's a whole lot better than not using it at all. So the rigid model with low variance means that it would perform similarly across different training data sets, high bias because it misses the nonlinear relationship. And, you know, that's something, by the way, this is going to come out in your data. Okay, you'll have millions of these data points. And so this is strictly a business feature. And so you can look at it as a limitation. What it really is it's a subtlety that you might miss in the data if you just tried to fit normally. That's basically bias and variance. If you look at the curvilinear line, it more accurately fits a true relationship, but it's overfit as it follows the data points too closely. So low bias is fine, but it has high variance because it's not going to perform the same with different data sets. So it's likely that it's going to perform poorly on new data. That'll come up. You guys are not going to have, if you get something strange in your model, first thing to look at is imbalance. Okay, like you've got you're looking for fraudulent credit card transactions. By comparison, you're probably going to have much fewer fraudulent than you are good ones. So be careful about an imbalanced data set. We're already, a couple of you, we're working to fix that. So second thing is you're going to have to realize that you're only going to have a snapshot of data. So it's not unusual if you get variations. Okay. Here's there. The solution for all of this is, of course, more data. But that's in a different world. Okay, so that is what we're going to do in technology. Everything else gets to be computer sciencey. I promised we would eventually go back to AI itself, because we stopped, let's see, we went into tech a couple weeks ago. Yeah, we were talking about technology applied to manufacturing. So now we're in the world of AI itself. This is the guts of it, right here. This is traditional programming. Okay. I give it rules, I give the system data, and it gives me answers. Machine learning is different. So okay, everybody that's had the disruptive class, you cannot respond to these answers, to these questions. The rest of you are winging it, okay? Okay, we've got supervised machine learning here. I'm inputting two features, feature one, feature two. Okay, here's the label, which is the result. Now, what you get is, I'm down here with machine learning. So I want to do this right here. This is right here in the middle. There is some relation between these two input features and the label. And what the system has to do, notice we're feeding it answers. What are the answers? The label. I'm feeding it data. That's my input features. And what I have to do is infer the rules. So what you get to do is you get to infer what is that relationship.
Multiplication.
Multiplication. Okay, how confident are you?
About 1 in 8. Or
Okay.
sorry, 7 out of 8.
Okay. That looks good, that looks good, that looks pretty good, that looks good.
That's the problem.
That's not so good.
Yeah.
Okay, that's not so good. Okay, -1 times 0. Okay, so what do I get? 1, 2, 3, 4, 5, 6, 7, 8, 2, 6 out of 8.
Yes.
Very simplified. I'm 75% confident. Okay, that's fine. Multiplication is correct. Now, notice this is probabilistic result. As I've said many times, and this will be true in the data set you guys are doing, you'll have probabilistic answers, not deterministic. Okay, so you look at this, you say, how do I increase this number to make it larger? Right now I'm 75% confident, give or take, that that's multiplication. How do I make that number better? Not you guys.
You could increase the input maybe.
Yeah, input, just increase your input, see what happens. Now, interestingly enough, you would hope that it improves this number. It may not. This could be a snapshot of the data set. What's really division, the other 100,000 features or 100,000 pairs will give you into division. But what we have here, this is it. All right, now look, suppose got this, you got a probabilistic result, got your label. What's traditional programming? Well, I'm going to define A, B, and C, input, A and B, C equals A times B, output C. Okay, very straightforward basic program. Define these, any kind of numbers, it could be integers, real numbers, whatever. I input the two values, so what have I done? I've got the data. All right, that defines the data. There's your rule, and I want to get the answer. Probabilistic or deterministic?
Deterministic.
Deterministic. Conventional programming is deterministic, which means, doesn't mean that C will always be the same. It means for any two values of A and B, I'm going to get an exact value of C. And deterministic is different. Now, does this mean that we have wiped out conventional, traditional programming with machine learning? We have not. There's a lot of deterministic answers that we're still doing out there. Accounting and finance, okay? All the P&L, profit and loss statements, all that's deterministic. Okay, now, when you look at this, you say, when you think about this, this means that you've got, the machine is learning from the data. Okay, in machine learning from data here, what's it learning from up here? The rules. Two totally different things. Okay. All right, that's the guts of it. So the code we write no longer dictates the choices, decisions our machines make. The data does. And that's just the way it is. Now, that gets real interesting as humans are being eased gently, somewhat to one side on writing code. If you're going to learn from the data, that's exactly what kids do. Feed them input data. Could be voluntary, could be involuntary. Have you ever seen baby with those little mobiles above them? Why are you doing that? Because they fix them, they watch them, they're learning as they go. It's fascinating. I think that people don't realize how important, when a child is in the womb, how important it is to, think positive thoughts. I've seen research on this, play music, not hard rock, that sort of thing. You pick that up when you're 20, all right? Okay, so here we are, supervised, unsupervised reinforcement. You guys know this already. With labels, without labels, find patterns. Reinforcement, you penalize this, you start the system at random, and you tell it to go do stuff, and just randomly. And it'll pick up patterns, and you give it points for doing it correctly or getting closer to correctness, and you give it penalties for not. Okay, and that's what we have. Now, have we done this here? We haven't done this one today, this class. Okay, good, the other class. All right, here's the deal. Karen Howe, she's up at MIT, and she got bored one day, and evidently she was getting questions on just exactly what is artificial intelligence. Well, she'll admit to you today, this actually should read machine learning here. But here's the deal. This is a great flow chart in her writing for what is machine learning. Is the system looking for patterns in massive amounts of data? Okay, yes or no? Yes, I come over here, great, you're in the machine learning. No, game over, you're at the wrong flow chart. Okay, that's pretty much the way Karen does things. Okay, so over here, once you decide it's machine learning, are you telling it what to look for? Do you have labels? Okay, yes, you got labels, that's supervised. No, puts you to another question. Are you trying to reach an objective through trial and error? Okay, if it's no, it's unsupervised learning. If it's yes, it's reinforcement. Now notice, It's just another way to get at the definitional slide we had before. Notice what happens. Supervised, reinforcement, and unsupervised all come into the same juncture here. Are you using deep neural networks? Okay. Now, if you say yes, welcome to the land of deep learning. What does that mean? You put it deep in front of supervised, deep in front of unsupervised, and deep in front of reinforcement. Deep means multiple hidden layers. Okay. Expanded neural network. If it's no, she writes, how boring. Just keep using the techniques like you got. There's no better flow chart than I've ever seen. And I think she just stroke of genius, you know? All right, then she did this. I think her students were really bored that day. Not gonna go through this with you, but here's the deal. Can the system see, hear, read, move, or reason? And she goes to this big flow chart. It is absolutely inclusive about how this goes. If you take the site and you go through the no's, you know, all of a sudden it goes no over here. If a system can't see, you've got a camera, okay? If it can, you go down here using computer vision to do image processing, okay? That's the way she follows through all this. Now, think about what our systems can do. Yes, they can see. You know they can hear because they can process audio files. Can they read? Yeah. Can they move? What am I looking at? Robots, which are nothing more than machine learning in action. And then can they reason? I'm looking for patterns just like we talked about. Absolutely. Okay, there's the definitions. There's artificial neural network, which we've talked about. And this is what we're already doing. I just put a few of these in here. We forget there's a lot of machine learning running in the background. Think about your cars. All of us, I'm sure, drive late enough model, even the faculty drives late enough model cars that have fuel injection system. All the students do. Anti-lock braking, anti-skid steering, auto parking. Do y'all have that little thing where you press the button and it parallel parks? Okay, that's the other students. No faculty have that. But think about this. That's nothing but machine learning. It's really simple, but that's what it is. So up here, spam filtering, optical character recognition. Facial detection, yes, but we do it poorly. Online dating, if you're on Match.com, you're in the world of recommendation engines. What's the difference between Amazon recognizing you and saying, welcome back, Kelly, here's a book for you, and saying, they notice on Match.com I'm 6'4", won the Nobel Prize. I get matches based on my input. Y'all know that thing about the two dogs looking at each other. It's an early cartoon when the computer world, the internet came out. There's these two dogs looking at a screen, and one looks at the other and goes, on the internet, nobody knows you're a dog. Welcome to dating. But the point is, that's nothing more than a recommendation engine. It's the same exact code almost that Amazon uses for, only Amazon has better data. Think about it. It's wild, wild west on the internet, guys. Okay, fraud detection, of course, customer segmentation, all this kind of stuff. Now, medical diagnosis is highly controversial because of the medical profession. We don't have time to really get in that today, this semester too much, but you've got that. High frequency trading, of course, good luck on Wall Street if you're a human. By the way, with high frequency trading, is there still a human in the loop? Yes. Front end or back end? Front end with the data you feed, back end looking at the results. None of the processing. You don't have time. Okay. Unsupervised, I stuck this in there because Google's been around. They've got Google X back then was their experimental branch. Now it's DeepMind. They put a little tiny neural network together, had 1 billion connections. They're, of course, much larger than that now. They've browsed 10 million randomly selected videos. Now, when I say randomly selected, I mean it. And the thing started coming up with cats. What surprised the engineers was it grouped lions and house cats, bobcats, all different types. And they went in there to look and see, and it was the shape of the skull, the ears, and a few other things. But it did not know what a cat was. The human in the loop had to decide what it had picked up. Same thing with a car back when Google, when Waymo was getting started. It picked up what a bicyclist was versus a car. That's good. And then it started picking up the hand signals. This means left, this means you're going right, this means you're slowing down. It was doing that by itself. Then it got to this problem. Dogs versus wolves. They decided to pick up something a little more difficult based on this. So they said, let's differentiate dogs from wolves. Well, if you got a Pekingese, that's pretty straightforward. German Shepherd, not so much. It was coming up with something like 95, 96% recognition. And a couple of humans went in there and they said, well, I think we see a problem. Most of the dog pictures, most of the dog images, what was the background?
A home. Indoors. Indoors in a home.
Indoors home for some of the dogs. What about the dogs that were the most similar to wolves?
Outdoors.
Outdoors. Well, the wolves were all outdoors. So what was the difference in the backgrounds? What were the wolves in? They were in the snow. And they were in the backcountry. But mostly it was snow versus grass. So they decided they're going to just switch the images. They found wolves on grass, dogs on snow, and it completely missed it. So the precision went down, or the accuracy went down to about 10%. Okay, what's the deal here? Human in the loop. This is you guys. You're going to have bizarre results coming out of your neural networks. And well, here it is, generative AI. The buzzword that's killing AI right now, GPT. It hallucinates. That's this. It come back and say, this is a wolf. I've got a Havanese about this big. I'm pretty sure it's hallucinating when it calls our dog a wolf. Okay? If I had a big German Shepherd, I might let that slide by. My point is, you guys, I told you, you're the start of this process and the end of it. Okay? Don't turn your back on it. In other words, don't just accept outputs of any sort of machine learning system blindly. The London Underground, if you've been to London, you've ridden the tubes. This is it. This is the whole section. So what they decided to do, they said, okay, here's the schematic of the tube, and here are our ridership numbers for the last several years. How many trains, how many people on a train? Now, you've got turnstile data, so you know how many people are coming in every time. And so you've got all these stations. Well, they just put it in there, unsupervised, said nothing to the system, and said, optimize it. Now, we've had optimization algorithms, as you all know, since the 50s. We're not creating new math here. All right, so what it started doing, really interestingly, it went to the inner city, picked up right here, this loop. Okay, now that's very close. You've heard of the city in London, the financial center? It's very close to that, where the highest ridership was. This is the Thames River, okay? And it started optimizing there and it moved out. Just exactly like a human would do. Except it would take how many of us, just this class, to help optimize that system? That'd be more than a class project. Okay, it was doing this in a day. All right. Okay, here's the deal. Let's take this up to FedEx or UPS. Y'all know they run a lot of trucks. They deliver a lot of packages. They have to do this efficiently. That's an optimization problem. That's all it is. Okay, Hartsfield International over here, the yield management system for the airlines, number of butts in a seat, okay, and run the thing. That's an optimization problem. Okay, I only mention robotics here because it's reinforcement. What we do is we just take robots and we say, go do something. And just do it randomly, and they'll go out and they'll stumble around and look kludgy. and then all of a sudden they start getting better. Okay, that's reinforcement learning. We do that with systems too. I'll tell you what, that's kind of, generative is such a mess right now. Since the fall of 2022, we have had, I'd say, 80% of the media talk about generative AI like it's AI. Okay, my point to you is this. First of all, in this class, and me personally, I don't differentiate between artificial intelligence and machine learning. We've already discussed that. I just say machine learning, deep learning with neural networks, these have not gone away. But according to the media, this is all we've got. That's not the case. So I don't want to do that right now. I want to do that at the end of the semester so I can blow it up. It's the media has really jumped on it thanks to the fact that everybody's using it. Okay, before that, just certain areas like it was all in computer science and students were not cheating and professors were not cheating. Y'all know the big hassle right now is students are getting chewed up for using generative AI, say in a certain school, and then they find out the professor's using AI to grade their tests, and they're just like, and I agree with them. That's just not right, you know? But you see where I'm going with this. So we'll come back to that. But they've got some real problems. Okay, here's what we do. You guys are white collar workers. You're going to look, listen, read, and write, and you're going to integrate knowledge. What's fascinating is we can do this with machine learning. What happens when technology impacts a service economy? What happened to agriculture when technology impacted agriculture? In 1800, what percentage of the workers in the United States were agriculture?
50%.
Yep, not 80, maybe 90, 1800. Okay, how many today? 2. Okay, 2%. Now, in 1900, what percentage of the workers in the United States were blue collar? That's probably about 50, because we still had a bunch in agriculture. Okay, today it's 15. That number will never get bigger than that. Okay, so now we're in white collar world, and AI has been hitting that since the 60s, but only in a software kind of progress, mostly in the last, say, 20 years. Now that generative AI is out there, now all of a sudden you're thinking, what do we do with the service economy? I've got 2% of the workers in agriculture, I've got 15 or so in blue collar, which means 80% for us, all of us in here in white collar. What do we do when that starts declining because of this? Well, here's where we are. I just put integrated knowledge first, and the easiest way to look at that, I love to see this the way that games are played. In 1992, this is Gary Kasparov here. He was the world's leading chess grandmaster. And in 1992, he beat IBM's Deep Blue program, and he stood up in front of the world and said, a computer will never beat a human in chess. 5 years later, Deep Blue cleaned him up. Okay? He stalked off, as a matter of fact, on national television, which is an absolute, watch him lose his temper. Okay, now, this is chess. Does anybody in here play Go? Okay. Chess has a lot of moves, okay? It doesn't even compare to Go, okay? Checkers is to chess like chess is to Go, only Go's more complicated. So it took till 2016, and Google DeepMind beat this gentleman here, who's the world's leading Go player. Now, guys, that was significant. We've never had another human champion in chess or Go. We still have human tournaments. And what's the real problem in a human tournament? Make sure that the humans do not have access to technology, like invisible earbuds, like hearing aids, or that's embedded in their glasses or something. It's like in the Tour de France, they X-ray every bike, because some of those guys are putting tiny little electric motors in there. They're about this big. Come on. Okay, so they do have unenhanced human champions, but it's because the system has just passed. Okay. Remember, anytime a system does a task equal to a human's out. Okay, the system that beat Kasparov in '97 is available for free on your phones now if you want to play chess. All right, so alpha geometry came out a year ago, 18 months ago. Again, Google DeepMind. They went to the International Mathematical Olympiad. Now this is tough. It solved almost all the geometry problems. Notice, it beat previous state-of-the-art algorithms by 15 answers. It has only gotten better since. I don't think Google's worried too much about that now. Who picks this up are the systems like Khan Academy. Okay, the learning systems will pick up this technology. This particular model had two. It had a logical model. It tried to find an answer traditionally, conventionally, and it had a large language model like GPT or Claude, and it generated out-of-the-box ideas. And it married up reasoning skills and creativity being out-of-the-box ideas, to explain it. Okay, robotics are fascinating to everybody. They're easy to see. They're scary because everybody thinks of Terminator. Okay, I mean, Arnold Schwarzenegger will be forever linked in with robotics. However, a lot going on. So back to the language part. This is kind of interesting. International languages, international instantaneous translation. You got earbuds. Pilots developing these desperately, as fast as they can. So you get a pair of earbuds. Now, if you want this thing to do translation, you got to have two earbuds. You get one, the other person has one. Okay? Well, now, of course, we can do it through a phone. You've seen those commercials? You speak English, the phone translates to Italian, the other person listens to it and goes back. Okay. Earbuds are even neater, okay, because you can just pop one in and just converse back and forth. Now, you got to clean the earbud when you get it back and don't let the other guy steal it, but you see how this will work. Starkey makes hearing aids. And Starkey does a great job. They put some machine learning in to do directional microphones. Okay, if you're in like a concert and it's really loud, you can get the noise down, or you can literally direct the microphones away from the front or whatever. That's pretty cool, but then they put in instantaneous translation into their hearing aids. So that's pretty unique. It's right now, it actually does work, but it's something that we're pretty much going to get away from having to worry about language. Now, I asked one of my colleagues over in foreign languages, what does this slide do for majoring in a foreign language? You guys, did y'all take foreign language come through here? They used to require that. Well, he said that basically, for just learning a language, you pretty much take it out. So basically, if you're Duolingo, you got a problem. You're on your way to being disrupted. But he said our last 2 years, you get fluent and you learn the culture and all this kind of stuff. So there's a difference between being able to stumble around in a restaurant or find a bathroom and being fluent. Okay, that was his point to me. All kind of apps, human resources, manufacturing, banking, finance, marketing, they're all over the place. Sports, shopping, but then you get to law. Now these are, any lawyer would look at what I just went through here and say, of course. Then I say, what about this? Well, Rolls-Royce got indicted for corruption a few years ago, and they had an AI startup called Raven, and it analyzed 600,000 of these documents per day. So it was looking for contracts. Junior lawyers examined 3,000 per day. This is multiple junior lawyers. So Raven went through 600,000 a day, fewer errors, it only cost $65,000, and you ended up with a big fine. Now, 30 million pages. Y'all understand this because we've automated electronic discovery. Explain this to me. This is a classic task to train junior lawyers. To analyze documents of any type, in this case it was contracts, learn and write briefs. That's how these men and women learn and move up. Okay? What are you going to do now? We don't know. If you're going to go into a consulting firm, PricewaterhouseCoopers, Deloitte, Boston Consulting Group, IBM Global Services, as a first day consultant, you're supporting someone on an engagement. That's how you learn. If that has anything to do with clerical, you're probably gone. Okay, so the point I'm trying to make is, first of all, you're not going to get this over to lawyers real well. Secondly, this is very important right here. Finding unknown unknowns. That's essentially what electronic discovery does. That's what Luminance does, and this is what we're talking about. That's pretty much gone from the law. And I am curious to know how we're going to train senior lawyers. That's not just my own curiosity. Have I talked about that with lawyers? Yes. Have I gotten any satisfactory answer? That would be a no. So there we are. Now this came up almost 10 years ago. Ross Intelligence picked up on IBM Watson. You all remember Watson that won Jeopardy? Okay, that was a deep learning, machine learning program. So Ross picked that up and used Watson. And this is a white shoe firm, a great big giant firm that handled bankruptcy. Okay? So they used Ross to do discovery, and they got rid of almost all their partners in bankruptcy because of electronic discovery. Well, then Ross got sued by Thomson Reuters. Now, you guys know what Westlaw is? Westlaw is digitized law going back centuries. Okay, so it's a gigantic database of previous court cases, global court cases. And so Thomson Reuters has owned Westlaw forever. That's their legal research platform. It's digitized. What these people did, they went in, bought a license to Westlaw from Thomson Reuters, and then used it to develop their machine learning program. That was their data input. Well, Thomson Reuters was very unhappy about this. So they called them up and said, can't do that. So you have to completely figure out how to build your machine learning algorithm again. Well, Ross couldn't do that. Moving target. So now Thomson Reuters does what Ross was doing. That's their division there. So Ross went bankrupt next day. This is what I'm trying to say. If you guys are developing a proprietary product using someone else's data as an entrepreneur, be very, very careful. You know, this is case in point right here. Agriculture, do not underestimate agriculture. Okay, it's one of the most technically advanced industry verticals that we have. It's well up there with finance. You guys know this. Self-driving tractors, drones, gigantic agribusiness. So insurance, of course, life insurance even more. Journalism, we're in a mess because, as you guys know, was it Sports Illustrated that came out that all their articles being written by AI, by generative AI, and they got in all kind of difficulty. A lot of these news writing bots now have been picked up, generative AI, and you have to wonder who's actually writing the articles. Of course, real estate, entertainment, and so forth. It's in our society, it's embedded. Now, deep fakes. Somebody tell me what a deep fake is. What's the definition?
Well, the popular example is they would take a picture and video from a popular celebrity, especially usually like, phone camera footage that they would, upload on social media, and then they manipulate the sound, the audio to make it say whatever they want, as well as the visual of the face speaking it. Sure.
Deep fake video, but an image can also be a deep fake. Transfer somebody's head or face on their bodies. But deep fakes are really frightening because now you can match up their facial expression, the way their lips and tongue move, their throats, their body language, and you get this.
That's fine. So, embarrassing, it reminds me, just once in Russia, ran into Gorbachev. He said, Mr. Movie Star, are you nervous? I said, no, Mr. Gorbachev. He goes, well, remember how much a polar bear weighs? I said, polar bear? He said, enough to break the ice. It's the last time I've ever seen Macau Gorbachev. What's up, TikTok? You guys cool if I play some sports? I love it. More for the audio experience. As much as the momentum. Hey, listen up, sports and TikTok fans. If you like what you're seeing, just wait till what's coming next. I'll show you some magic. It's the real thing. I mean, it's all the real thing.
All right, you got 3 clips of Big Bad Tom. Which one's real? That is a real image of him, by the way. 9. They're all send-ups. You notice they overdid his gestures. You know how he does with his teeth. What if they hadn't? What if they had not put all the extra flourishes in there? I would have no idea if those are real or not. Now, translate this to politics. You're running for office, and somebody has captured enough video of you to have you saying something exactly the opposite to your beliefs or what you're running on. And it looks exactly like it's coming from you. Same gestures, none of the send up with Tom, you know, the pratfalls and stuff. Think about this. What if you put one out on your professor? All of a sudden it shows up on Panopto. Hey, everybody made a 98 on that test. You have to think about how this works. It is very frightening. Now, we'll close on chatbots. Look, it's great to say we're going to slap machine learning on chatbots. If I had to pick personally, one thing that made me more insane than anything in this world is talking to a chatbot. Once you get off script, you're in the twilight zone. They're still kludgy. They're there to do what? Get rid of call centers. You want to get rid of humans on the other end of the line. They always talk about 80-20. The chatbot should handle 80% of the queries, 20% escalate to humans. Personal opinion, it's 10-90. They can handle 10% of your query if you're lucky, and you need the other 90% to talk to a human. Now, the interesting thing about chatbots is, for some reason, these lunatics are programming these things to make it very difficult to get to a human. Y'all tried that? Please, give me a human. Okay? Exclamation point, 10 of them. It's just really good. You have to keep after it. So, we're not there yet. It is possible to get AI as a service. All the major cloud companies will provide that. Lower risk. This is an entrepreneur's dream. Okay? And then we get to AI assistants. Jarvis. Everybody knows about Iron Man. And we will talk about him on Wednesday. See y'all then. One will tech.
You have a bad encounter with a chatbot in between the 8 a.m. class